Hello everyone, welcome to third video of EV motor sizing short course. This course is part of basics of EV simulations using Ansys. Let's have a quick recap of what we learned in video number 1 and 2. In the first part, we learned about fundamental principles of electric vehicle motors, their types and different materials, and we have also seen an open view or render image of the motor, how an EV motor will look like. In the second part, we discuss about how to decide about speed and torque and power rating of EV motor. So once we have come to a conclusion of speed, torque and power rating of a motor, the next step is the motor sizing with fundamental design equations. So now let's see what is included in the course. So these are the learning aids which I am going to use, and these are similar to the video number 2 which we have followed. So what you are going to learn in this video, you are going to learn about fundamentals of motor operation and construction, fundamental equations of motor sizing, specifically for permanent magnet synchronous motor, basics of power converter operation for a permanent magnet synchronous motor, and analytical design of PMSM motor with Ansys RM Expert and Maxwell 2D. So these are the things you are going to learn in this video, and if I try to connect with the previous videos, we have already seen some of the fundamentals of motor power estimation. So those motor power estimation can be referred here, and then you can start the paper design of the motor. So let's move ahead and learn about fundamentals of motor operation. So what are the minimum things required for any motor to work? So for any motor to produce rotation, or we can say torque and speed, there are minimum 2 things required. So the minimum 2 things are basically the flux, or we can say the magnetic field, and current, we can say the electric field. So the entire motor theories are dependent on 2 things. One is the magnetic field and the other is electric field. So the electric field and magnetic field are both required in order to produce the speed and the torque. Now if I draw a simple construction of a motor where you have one pole over here and we call it as N pole, and another pole over here we call this as S pole or south pole, the magnetic field are established from north to south. So the field lines can actually provide some force on a current carrying conductor placed in this magnetic field. So how do we have a current carrying conductor placed in a magnetic field? So if I draw a conductor like this current carrying conductor, if it is placed in a magnetic field, then it can produce the required force, and this conductor will move physically according to the force. Now this force is basically the force acting due to attraction and repulsion. So basically what happens inside a motor is, whenever you have a current carrying conductor which is carrying the current in up direction from bottom to top, this will create its own magnetic field. Now this magnetic field and the permanent magnetic field will interact with each other and can produce the force. So the interaction between 2 magnetic field is very much important for the motor operation. So the interaction of 2 different magnetic field is a third part where the motor operation is going to be considered. So one single coil which is placed like this, or I will not call this as a coil, but it's a conductor. Now if there is one conductor and we need to see how we are going to provide this current, how we are going to supply the current in this conductor. So the supply in this conductor can be made through a return path where the return conductor is like this, and this single turn coil can actually be connected through the positive and negative supply of a DC voltage through a commutator, and this becomes a simple operation of a DC motor. So a DC motor operation is very simple, where you have a current carrying conductor placed in a magnetic field. It is going to experience the force, and basically if you have this coil which is allowed to rotate, so now this coil is a construction, and if this coil is allowed to rotate, how this coil can be allowed to rotate? There has to be some rotating arrangement. So then this coil can actually make turns. Now remember, whenever the N pole and S pole are basically going to be fixed, the direction of the current can get reversed due to the commutator action, and because of this the coil can experience the rotations whenever placed inside the magnetic field. So this is very simple construction of the motor. Now coming back to the EV motors, what kind of construction they have. So if I explain you about an EV motor, basically they are brushless DC motor, and let's understand about what is a brushless DC motor. It is very much required that you know the action of a commutator first to know about the electronic commutation for a brushless DC motor. So if I show you the arrangement of a brushless DC motor through this animation is basically created by Renesas Electronics. It's a semiconductor company which provides the motor driver semiconductor chips. So they not only provide the motor driver semiconductor chips which will be based on intelligent control, but they also provide some fundamental learning about the motor. So the power converter engineer will also basically work on the motor fundamental operating principles. So if you have closely look at this, the rotor is basically a fixed permanent magnet rotor, and the N pole and S pole of the rotor are not changing because they are permanent magnet. Now the stator is basically a winding or coil, is a three-phase coil. So there are three phases on the stator poles. So this is one of the stator pole. How the stator pole is created? Basically this stator pole is an electromagnet. What is an electromagnet? Electromagnet is the material whenever excited through electrical current, it is going to produce the magnetic field. So this electromagnet are basically going to produce the required magnetic field. Now let's pay attention to the pole number 1. So here there are three poles, pole number 1, 2 and 3. They are 120 degree apart from each other, and they have three phase winding. Now let's take the case of the pole 1. So whenever the pole 1 is energized with the current flowing in the downward direction, the orientation of the magnetic pole is such that it produces N pole over here on the bottom side and S pole over here and the top side. So this is the downward direction of effect of the current flowing in the downward direction. So you can see in the animation, whenever the current flows in the downward direction, N pole is created over here and the S pole is created over here. Similarly, whenever the current direction is outcoming, the N pole and the S pole changes. Now the same happens with the other two poles as well. So this is how a three-phase coil is excited. And basically if you see the coil connections, if I simplify the coil connections, it will be like this is the first pole winding, this is the second pole winding, and this is basically a third pole winding, and they are connected through a star connection. So because they have this common points, so these are the common points where end of all windings are made common. So this is a star point or a return path, and these are the phase windings where the current will be either incoming or outgoing. So based on the windings which are excited, the N pole and S pole are created electromagnetically. Now those electromagnetically created N pole and S pole will basically generate attraction and repulsion related forces in the air gap available over here. So these electromagnets will try to catch up whenever there is an S pole. An N pole is going to attract, the same S pole is going to repel. So the attraction and repulsion happens in such a way that the rotor actually rotates in counterclockwise direction. So if you have understood that the N pole and S pole available on each and every pole of a stator are created intentionally, right? So if this pattern of excitation is not followed, the motor will not be able to maintain its motion in a typical direction. So this excitation sequence is very much important, and it is also important to know the rotor position for a brushless DC motor. So this is the fundamental operation of a brushless DC motor, and as you can see here, the electromagnets are basically created by windings, right? So when we talk about the conductor, coil and the winding, basically they are the higher order forms of a current carrying conductor. Now if I show you an actual picture of the motor, so this is just for concept and this is not going to be replicating the actual motor, right? We are going to see now in Ansys software how does an actual motor will look like. So here I am referring to another render image from Nidec Corporation, which is basically a motor manufacturing company. So motor manufacturing company like Nidec have developed a brushless DC motor for hard drive application, and this is the image of hard drive printed circuit board. And basically what you are able to see, these are the stator part and these are the stator coil which remains fixed, and the rotor is basically this disc, and there will be permanent magnet mounted over here. So this is a permanent magnet rotor, and the difference between this concept and this product is basically here you have the rotor inside the stator and here you have the rotor outside the stator. So many applications consider the rotor which is outside, and this is just a simple application of a hard drive. So what you see over here are the stator number of poles, and where you have the winding, where you can see the copper is wound over here like this, and here you have the permanent magnets. So the stator poles and the rotor poles will interact with each other and produce the required torque and speed, and this is the fundamental motor operation. We can actually dive deep into this and go on talking about the motor operation and talk about what is the purpose of that type of construction of that motor, but during this short course we are not going to touch upon that part. So let us now focus on the fundamental sizing equations. So what are the fundamental sizing equation? What I need to decide, let's say I have the torque, speed and the power values. How do I satisfy all these values based on the motor material and the dimension which are available to us? So application specifications are very much important. From an Excel calculator we can take the values of torque, speed and power, and basically the vehicle dynamics team as a part of a large engineering team can come up with a very detailed data on the vehicle speed, torque requirements, and this can include the braking requirements as well. So we are going to learn about how motor can be constructed such that it can match the load demand. Now what do we mean by the construction of a motor? The construction of a motor refers to the dimensions and material. So basically motor sizing activity is deciding on dimension as first part and material as a second part. So if you have decided the dimension and the material together, you can basically go back to your calculations and follow that whether your torque, speed and power requirements are matching or not. And this is basically not a simple calculation as this. There are fundamental difference between a design and a calculation. So design is basically the choice along with the calculation, right? So you need to assume many parameters over here in the design, or basically the sizing of a motor. And let's understand the very fundamental thing which is known as electric and magnetic loading. As I explained in the previous slide, the magnetic loading basically refers to the flux part of motor, and electric loading refers to the current part or coil and winding part of the motor. So the electric and magnetic loading is very much important to be understood for sizing of any motor. Now, what do I mean by sizing of a motor? Let me give you another application where, let's say, if you have a high story building, and on, let's say this is 3-story building, and on the top of that you have a water tank basically supplying the water to all the houses of this building, and below the ground level you have a ground water tank. So this is the ground tank and this is the overhead tank. Now, in order to pump the water from ground tank to overhead tank, you will require a pump which is going to be driven by a motor. So let's say this is the pump and motor assembly. Now, what should be the size of this motor such that the piping which is done from the ground tank to an overhead tank is going to provide the water to all houses? So what are the parameters you need to take care? You need to take care of the height, you need to understand about the flow rate, you need to understand about the diameter of the pipe, and there are many other factors as well. So if you know the fundamentals of your application, it becomes easy for you to then next step is the sizing. So the sizing becomes easy if you have the torque, speed and the power requirement along with the limit of the volume. So if you have any constraint on the volume, or if you have any constraint on the temperature, operating limits of the motor, then this can be the other inputs as well. So if you consider the electric and magnetic loading, that is the very first step of sizing of a motor. Now, as I explained in the previous slide, the force acting on a current carrying conductor placed in a magnetic field B, and the length of the conductor is L and the current is I, the force will be experienced by the conductor, and that can be written as F equals to BIL. Now, how do we actually get the torque from the force, right? So it's not going to be only one conductor carrying a current enough for the motor. We will have a group of conductors. Now, group of conductors will be placed on a rotor, and this rotor element will have some diameter, let's say D, and the radius can be D by 2. So the force multiplied with the radius will result into the torque. So the motor torque can be calculated from force into radius. So these are very simple equations to understand, to start understanding about the sizing of the motor. Now, if I consider the shear stress which the rotor is going to experience, it can be represented as this equation where it's product of B into A, where B is basically the magnetic loading, or we can call it as a uniform magnetic field or magnetic field density in Weber per meter square, and E is the electric loading. We are going to learn about electric loading in the next slide. The force F is in newtons, and if you multiply the radius by meter, the force will be Newton meter. I is basically the RMS current flowing through the current carrying conductor, and L is the wire length, T is the electromagnetic torque, and as I said, D is represented as a rotor diameter. So this fundamental equation is going to be a simple equation where you have a stator and the rotor, and this stator and rotor will produce together the required force. So let's say if you have this as a stator arrangement, and let's say there is one slot over here, and this is the overall rotor, and if you consider the coils or windings which are placed over here, then this rotor part is going to experience the force, and all this rotor conductors together will produce the electromagnetic torque. So the B times A is basically the electric loading times magnetic loading, which defines the shear stress available on the rotor. So moving on to the next slide, we are going to now talk about the fundamental torque equation. So how can we actually calculate the torque which is given by force, right? So if we replace the force values by certain parameters which are the design parameters, then we can write the equation of the torque in this format. So this torque equation basically involves AB, and D is the diameter, and this torque is proportional to the square of the diameter. L stands for stack length. So LSTK stands for stack length, and we are going to see the terminology is KW1, which is basically the winding factor, fundamental winding factor. So 1 stands for fundamental thing. Now what is A? So A represents actually the electrical loading, and the electrical loading can be determined as total ampere conductors. Basically these are ampere turns divided by the air gap circumference. So how much is electrical loading per unit area? So that is what is called A. And basically if you have m number of phase and number of turns per phase as NPH, and I is a current flowing through the each conductor, then this 2m into NPH times IRMS divided by pi d is going to be electrical loading, because we are going to have 2 wires of a coil. So that's the factor 2. Now if we consider the next important parameter or the next important equation, which is basically the torque ratio volume. So the ratio of torque to the rotor volume is basically called TRV. So TRV is one such important parameter for the sizing of the motor, and there are other important parameters such as shape ratio, which is usually called as L by D, or sometimes it is also referred as L by D square or L square by D, and so on, depending on the type of the motor. This shape ratio is also a very important parameter for motor design. Let's focus on the TRV. Basically it's a torque ratio per unit volume. So torque ratio per unit volume of the rotor. So what is the volume of the rotor? It can be determined from over here. So pi times D square divided by 4. So if I exclude these terms, 1 time of pi D square by 4, that is going to be the ratio, that is going to be the area, and if we multiply with the stack length, that is going to be the volume. So basically the volume of a rotor, which is going to be like a cylinder like this, and if it has length of L stack over here, and if it has the radius or the diameter which is D, then we can have the volume of this cylindrical construction as pi r square, which is basically pi into D square by 4. So if I replace R as D by 2, it will be D square by 4 multiplied with length. So this is going to be the overall volume of this cylinder. So here, if we take the torque with the rotor volume, then TRV becomes this value. And basically if you consider all this as constant, it's fundamentally the multiplication of A and B, which is electric and magnetic loading. Let's see other fundamental equations as well. This E is basically the EMF produced, or we can call it as a back EMF, which is basically, the full name is back electromotive force produced in the winding, and it can be equated like this. So here the flux equation is B times area. So flux is represented as flux per pole, and it is multiplied with area, where we can write the equation for B is phi divided by A, and this area is basically pi dl divided by number of poles. So here we are representing P as number of pole pairs, and 2P will be equal to number of poles. So this is the equation for the flux per pole and EMF induced in the winding, and based on this fundamental sizing equation you can finally decide about the D, L and A and B values. So you can actually decide about what should be your design choice for number of turns, for current, diameter and so on. So basically torque ratio volume is one such parameter, and other parameter is the shape ratio, which is popularly known as length divided by diameter. So if you calculate these parameters, the next step is to realize the performance of the motor. Now, can we realize the performance of the motor just from the dimensions? No. So there are two important things to be considered. One is the dimension and the other is the material. So when you are considering some value of current, when you are considering some value of flux per pole, basically you can achieve the value of the current and the flux based on the electrical and the magnetic material which is present in the motor. So the materials and dimensions together will help to fix out all this and construct a motor.